what we just did in the last section was graph transformations. Right, so that's where we started with a function and then we like shifted it left or right or up or down. And what we're going to do here is graph polynomials, which involves some different techniques. But before we do, I usually like just to remind ourselves what a polynomial is. I know we kind of already mentioned this a little bit, but let's really get it out there in the open and make sure this terminology is really important. So this first box is just a bunch of terminology, and you need to know this stuff because when I say like, you know, that leading term is blank, or when I say the leading coefficient of this thing is blank, you kind of need to know what those things mean, right? And so polynomials have this form, and if you remember what makes it a polynomial is that all the powers are whole numbers. They're whole numbers and they're positive. And so that's what this says, where n is a non-negative integer. So that means that all the powers in there are whole numbers and they're not negative. We call all the a's in there, so in this thing, all the numbers out in front of the variables, we call those coefficients. I think that's nothing new. None of this is new, but we just want to remind ourselves of it. We call the last term, notice how this last term doesn't have an x with it. Right? There's no x with that last one, and that's the constant coefficient. So it's just whatever's on the end there is usually just a number. We call the first term, the first coefficient, this an, the leading coefficient. And that's an important coefficient because it's the one that's attached to the biggest power. And so the biggest power, whatever number is out in front of that, we call the leading coefficient. And you'll see that has an important implication for graphing. And then the entire first term, both of those things together, we call the leading term. And this is just kind of laying one out for you, right? So this is an example of a polynomial. We can see that all the powers are whole numbers. They're not negative. We can see that the coefficients are being labeled as the numbers in front, right? We've got the constant term at the end. Oh, something I forgot to point out in the top here is that we call the function degree n. And so you can see that n is the biggest power. So whatever the biggest power is, we say that thing has degree, whatever that power is. So in this first one, for example, the biggest power is a 5. And so we say this is a degree 5. And that's important because, again, that 5 really controls the whole function because it's the biggest power. Right? When you plug a number into this function, it gets raised to the 5th power right there. And that's going to be the biggest number. Especially for big numbers. Like if we plug 1,000,000 into this, 1,000,000 times 7 is only 7 million. But 1,000,000 raised to the 5th power is a massive number, right? And so this 5th power really takes over the function in the long run. All right. Any questions about those? Any clarifications or anything like that? You haven't heard like any other terminology or anything like that, right? I think this is usually pretty standard. Here's just another couple examples down here. So if the polynomial has degree 0 or 1, that means it's a straight line. And so for example, here are two examples of degree 0. Right? We see p of x equals 3. That's a degree 0 because the biggest power in there is 0. Right? It's kind of like we have an x to the 0 in there. What's x to the 0 again? 1, right? Yeah, so 3x to the 0 is just 3 times 1, which is just 3. And so this is a degree 0. A degree 1 is a linear equation, right? This is y equals mx plus b. And then degree 2 looks like a quadratic. That looks like a parabola. We can see that. Polynomials of degree 2 are parabolas. And then as soon as you get something higher than degree 2, it starts getting more complicated. And if you take calculus, what you'll see is that every time you add a power, it adds a curve in the graph. And so every time you add a power, it makes it curved more. And so the more powers, the more curvy it is. But the really nice thing about polynomials is that they're continuous. Graphs of polynomials are continuous, which means that there are no breaks in the graph. If you trace your finger along a polynomial, like these two examples down here, if we trace our finger along this, we don't have to lift our finger off the page at all. right? It's continuous. The continuous kind of means what it sounds like. It continues in all directions. And so here are some examples of things that are and aren't polynomials. And so we can see that the things on the right certainly are polynomials because they're continuous and they don't have any jumps or breaks or anything like that. And so these things on the right are continuous polynomials. The things on the left are not polynomials. And the things on the left are not polynomials. We can just visually see because it's not continuous, for example, right? There's a break in this one and there's a hole. And so if we were tracing our finger along this graph, we would have to pick it up off the page at this point right here to go up to the next piece. And so that's indicating it's not a polynomial. And at the hole, we'd have to kind of lift it up and jump over the hole and keep going. And so there's two reasons why this one's not a polynomial. This one looks like it's continuous in that there aren't any breaks in it, but it has a cusp, which looks like this, and a corner, which looks like this. And cusps and corners are indications that we don't have whole-powered exponents. Whenever you have a cusp or a corner, it means that your exponent is not a whole power. And so I know that's, I'm not going to ask you that question, but that's how I know that those aren't polynomials, because those are indicating to me that we don't have whole-powered exponents. And so these two examples on the right here are examples of non-continuous functions. I don't know what they are, but they're definitely not polynomials. I can come up with a couple functions that might fit those, but all I know for sure is that they're not polynomials. Questions? Just some terminology on this page. Then we want to start graphing this stuff. All right, and I'm going to say things like, all right, you take the leading coefficient. All right, this is a degree 4, blah blah blah, and you just want to kind of come back to this and know what those different terms mean. Is that all right? Okay, so let's graph some. So let's start with some boring stuff. I'm sorry, not boring. It's never boring. It's awesome. What I mean by boring is just stuff that we've already done, kind of. Let's start with something we've seen before so that it makes sense to us when we do something that's a little more complicated. What's a monomial? What's the word mono mean? What's that prefix mean? It means one, yeah. What's another word that has that in it? I guess there's like monowheel. What's another word that has mono in it, other than the disease? But I'm sure that disease has something about it that there's just one of. I'm sure. Monotone, yeah, right? What does a monotone mean? It means your talk in one tone. Your tone does not change, right? One tone. So anyway, mono means one. And so monomial, which is at the top of this page, that's a polynomial where you only have one term, right? One-termed polynomial, monomial. And so things like that are listed here. X squared, x cubed, x to the fourth, x to the fifth, those are monomials because they each only have one term. And those are, we already know how to graph those. These are like the base functions that we talked about in the last section. Right. And so that's kind of just another like vocab thing more than anything. But when we go to graph these things, there's two different ways we're going to do it. You can either, number one, use things from the last section about transformations. Right? If it's a simple enough monomial, we can just use a transformation and do what we did in the last section. Right? And so this method is what we did last time and the time before it. And so we'll practice doing that real quick. But then what we want to do really is graph more complicated polynomials that are not just a single term. We want to do not just transformations. We want to be able to start with any polynomial and get a general sketch of what it looks like. And so that's what's going to be done on the next page. Next page or pages? I guess next 2 pages. And so keep in mind that, we're going to do these two different ways. The first is kind of a review. The second might be a little bit new. And so the first one is on this page. If a function is simple enough to graph, if it's just a monomial, if it's a transformation of a monomial, I should say, then we don't really need to do any work. We just kind of know how to transform them using the stuff from the last section. So like, for example, we've got x minus 4 squared here. What kind of transformation is this? What are we transforming in this first one? What graph, though? What's the base graph? Yeah, x squared, right? So we're in this one, our original function is x squared. And what did you say we're doing to it, Manuel? We're moving it to the right 4. So we started with x squared, and we plugged in an x minus 4. Right? That's how we're thinking about this problem. And so this is a translation to the right 4 units. Right? And so we're going to move x squared to the right 4. And so, it's an easy enough graph. We just kind of do it the way we did last time, which is we start with x squared, and we just move it to the right 4. And so instead of being at 0, 0, it's over here at 4, 0. So that one's no big deal. What about this next one? Take a second and think about this next one. There's three transformations going on in this next one. Okay, so let's just so we're on the same page. What are we transforming? What's the base function? Yeah, so this is an x to the 5th transformation. But we've got a bunch of things going on. There's a negative sign out front, there's a 2 out front, there's an x minus 2 inside of it. And so there's 3 things that are happening. And just take a second and think to yourself, what are those 3 things doing? So what's the negative sign do? Flips it, vertically, good. Not horizontally because it's on the outside of the function. It's a vertical flip. So that the negative sign is going to flip x to the 5th vertically, i.e. over the x-axis. The 2 is what we talked about at the start of class. What is that? It's a stretch because it's bigger than 1. If it was a fraction, it would be a shrink. But it's like we're taking x to the 5th and we're multiplying it by 2. And so it's going to stretch it vertically. So that's going to be a vertical stretch of a factor of 2. And then the minus 2, which is in... Question? Yep.
So if we see something like that, we should take it all separate, like the negative separately and the 2 separately?
Each one does a different thing, yeah.
So it wouldn't be because negative 2 is less than 1, so you wouldn't take it.
Oh, I see what you're saying.
Yeah.
But if you look back at that page, so the question was, negative 2 is less than 1, so why isn't this a shrink? In order to be a shrink, the number out front needs to be a fraction. It needs to be between 0 and 1 without the negative sign. And so yeah, we think about them in pieces. The negative sign is its own thing, the 2 is its own thing, and the minus 2 is its own thing. So we think about them in pieces. Yeah, that's a good point. And so the negative 2 shifts it to the right, right? So it shifts it right 2. And so we've got those 3 things going on. X to the 5th. I'm going to draw the base function over here, and I'm going to try to draw it in a way that accentuates the stretch in the next one. Right? It's kind of hard to draw the stretch sometimes because you need to have something to compare it to, right? So the way I'm going to do that is I'm going to try to draw my next graph more stretched out than that, so steeper. I'm going to try to draw those lines steeper in my next one. But it's also going to be flipped upside down and shifted to the right. Right? So we're going to flip this thing upside down, so it's going to be going down instead. It's going to be stretched and moved to the right. And so I think my best impression of that might be this. And I know the x-intercept because it just moved to the right 2, right? It used to be at 0 and it moved to the right 2. And again, I tried to draw it more stretched out. I tried to draw it steeper than the other one to indicate that vertical stretch. Yeah, I'll leave it at that. Note that we would want to find the y-intercept if this was a real problem. But I want to move on to the next page, which is the new stuff. This is kind of review. But I did want to point out, I usually like doing this because just to point out that these are polynomials. These transformations of these things are polynomials. If we did the 5th power and we did this all out, like we expanded this, it would look like a polynomial that looks just like something on the first page. What's the degree of this one? What's the biggest power going to be, you think? 5, yeah. So that 5 is telling us it's degree 5. And this one's going to be a degree 2. But they're just factored. They're in factored form, right? It's like a factored version of a polynomial. Okay. Let's graph them. That's on the next page here. Let's graph them. Let's graph not boring ones, not monomials, not transformations. So let's look at that. The first page got a lot of words on it. And it's really just a guide. It's trying to guide you through this stuff in case you really need it. But if we let's just please just take a second and try to understand this, it won't be as daunting as it looks like. Like when I look at this page, it just looks very daunting to me because there's a lot written down. But it's really not that complicated. There's 4 steps. And what I've done is I've repeated the steps. I copied and pasted this thing from the book, which is fine, but then I tried to write out the steps in my own words below it. So let me just start by saying that all this stuff here is just re-explained down there. So it's repeated, so it's half as much information as it looks like. And let's just take a second and figure out what each thing's telling us. So if we want to know what a polynomial looks like, right, and we already know it's going to look something like this. It's going to look something like these ones from the first page. Let's look at the characteristics of this. It's got some zeros, and by zeros I mean x-intercepts, right? Each one has a couple x-intercepts. There's some bumps in it, but the bumps are somewhat controlled by the x-intercepts. In other words, if I know that the graph crosses, I can't really zoom in on this one. If I know the graph crosses at those 2 points, then that means that the graph either goes down below those 2 points and touches, or it goes up and comes back down. And it's easy to figure out which one of those does by testing a point in between there. And so if we just figure out what those zeros are, and then test a point in between them, we can figure out what that bump is, whether it goes down or up. And then the ends, see how this one has the ends pointing in opposite directions? This one has one end pointing down and the other one pointing up. And this one has them both pointing up. That's because this one is an even function. Even degree is what I meant to say, not even function. And that's because this one's an odd degree. And so the degree tells us whether or not the functions are pointing in the same direction, the ends are pointing up or down, or whether they're pointing in opposite directions. And so that's what this page is telling us. Let's go through these steps and work out what this is saying. So the first thing we do like I said in that last page, the first thing we do when we graph these things is we want to factor the polynomial and find out the zeros. The zeros are also known as x-intercepts. And then what we do is we test a point in between each one of those intercepts to decide whether or not the graph goes up or down. And then the end behavior, to determine the end behavior, that's what's being shown in this box right here. A function either has an odd degree or an even degree. Notice that the odd degreed ones both point in opposite directions. Either the bottom piece goes to negative infinity as x goes to negative infinity, or they both go to positive infinity, right? They're pointing opposite ways. And this is the same thing, just switched, like this, right? And so the first one happens if we have an odd degree with a positive coefficient. And if we have an odd degree with a negative coefficient, we get the second one. But all of this is based on the first term, right? It's all based on this very first term. And, this is a very confusing looking box too, but all it's trying to say is, if we have a polynomial of this form, we look at the first term. If it's an odd degree, we're in one of these two situations. If it's an even degree, we're in one of these two situations. And then if it's a positive number or a negative number, depends on whether or not we're in one of those two, right? And so if it's an even degree, both the ends point in the same direction, and if they point up, it's a positive coefficient, and if they point down, it's negative. I feel like I've already talked too much, and we just kind of need to look at one. Because the last step then, once we have all that information, is we just kind of put it all together, we plot the intercepts, we use the information in step 2 to draw the in-between points, and then we use the information in step 3 to look at the end behavior. Anyway, this is really just a reference page. Let's have this handy when we look at the next graph. Oh, actually, there's one other thing I'd like to share with you. The way I remember these end behaviors, or an easy way to remember it, if this is really confusing, is this graph looks like x cubed. Right? This is like an x cubed kind of shape. An x cubed has an odd power and a 1 in front. It has a positive coefficient. This one looks like minus x cubed. Right? If we flip this one upside down, and this one has an odd power and a negative coefficient. Right? This one looks like x squared. Both the ends point in the same direction. X squared has an even power and a positive coefficient. And this one looks like minus x squared. And that has an even power and a negative coefficient. And so if you just kind of remember that those 4 things look like those 4 graphs, it kind of helps you keep this straight in your head. Does anyone have any questions before we look at one? I think if we look at one, it'll clear things up a little bit. If you have something that's on your mind right now, I'm happy to answer it. Okay, let's look at one. So let's graph this polynomial. So use steps 1 to 4 from the previous page to graph this polynomial. So the first thing we want to do is figure out where it crosses the x-axis. We want to know where to put points along here. And so that's where we factor and figure out where the zeros are. So number 1 says factor. How do we factor this thing? What's the first thing we can do to factor that? It's a cubic, so we don't really have like a good method there, but there's something in common in all those terms. What can we pull out of there? Yeah, they all have an x, right? There's an x in each one of those. And so we can factor an x out. And this is directly from the factor section. And then once we do that, we have a quadratic that we can factor, right? We can factor x squared plus 2x minus 8, and we can factor that into x plus 4, x minus 2. And we want to do that because this helps us figure out what the zeros are. This literally, we can just pick them right out of here. So we think, okay, the function, the original function, equals 0 if this one equals 0, this one equals 0, or this one equals 0. If any of those 3 things is 0, then the whole function ends up being 0 because you multiply by 0. And so we get 3 answers out of that, right? So the x-intercepts are x equals 0, x equals negative 4, and x equals 2. And so I know it's going to cross the x-axis at those 3 points. Does it make sense why we do that? I get questions like about that sometimes. Like, why is it that if we want to know when this is 0, we set each piece equal to 0? Can anyone explain that? Why do we set each separate piece equal to 0 to know when the function itself is 0? Why does that make sense? So the way I like to think about it is if we want this to be 0, we want x times x plus 4 times x minus 2 to be 0. The only way we can multiply three things together and get 0 is if one of those things is 0. Right? Either x has to be 0. If that's 0, it cancels out the other one, makes those 0, right? If x plus 4 is 0, it cancels the other two out. And if x plus 2 minus 2 is 0, it cancels the other out. So if any one of those individually is 0, it multiplies the others and makes them all 0. And so that's why we take them separately and see when each piece is going to be 0. And we get 3 answers out of that. Any questions about that at all? That's kind of an important thing. And so before I do anything else, I'm going to put those on the graph. I don't know what the graph does yet, but I know it's going to touch right here at 0. It's going to touch right here at 2. And it's going to touch right here at minus 4. I just know it's going to touch those 3 places. And now what I want to do is just fill in the pieces that are in between each one of those. Just fill in the different pieces in between them. Questions so far? So that's step 1. Step 2 says test some points. Let's make a table of values and test some points in between all the points that we just found. So we'll make a table and we're going to test some values in between all of these. I'm probably going to ask you to try this next one, by the way, so I hope you're focusing in on this one. It'll give you a good practice on the next one. So number 2 says create a table of values that are between these numbers. Between those found in 1. So I'm going to make a table here. One of our numbers we found was -4. One of them we found was 0. And one of them we found was 2. And I want to test some numbers in between those to see what happens. Because I know the graph touches at -4 and 0, right? But the question is, does the graph go up and then come back down and touch 0? Or does it go down and then come back up and touch 0? And so I'm just going to test a point between them. If it's positive, it goes up. And if it's negative, it goes down. But I don't know which one yet before we test one. Right? So I'm going to test, say, -2. That's right in between them. And then between 0 and 1, I'll test 1. When I plug a -2 into the function, you get 16 out. You can think about that on your own, but when you plug a -2 in there, you get 16. And so what that means is, this is a positive number. And so that means we know the graph is above the x-axis between these 2 points. Between 0 and -4, sorry. Because this is a positive number, that means the graph between 0 and -4 has to go up to 16 and then come back down to 0. And so I know that this first piece, is going to do this. It's going to go up to 16 and it's going to come back down to 0. Yep. This?
No, the last thing.
This. So 0 and -4. This?
No, it was that. So in between 0 and -4 is and.
Oh, it's an and sign, yeah. Let me make that a little more legible. Questions about that piece? Right, I know it touches at -4 and 0 because those are the zeros. We got that from part 1. And then I plugged in a number between them and saw that it's positive. And so I know it has to go up to 16 and then come back down to 0. All right. And then we're going to do the same thing here. So the question is, between 0 and 2, does the graph go up and then come back down to 2? Or does it go down and then come back up to 2? And so I'm going to test 1 and see. And so when I plug a 1 in, g of 1 ends up being -5. Right, we'll get 1 plus 2 minus 8. And so g of 1 is negative. So that means we're below the x-axis. And so that I know on the other piece, we're going to go down to -5 and then come back up to 2. Questions? Why don't I need to test a point past 2? What's going to happen on the outsides of this? So -4 and 2. I'm not going to test any points out here. Any thoughts on that? Well, it does something out here, right? This graph is either going to go out or it's going to go down.
Oh, it's gonna.
Does anyone know how? Anyone think, Jackson? Yeah, so these end pieces have to do with the end behavior, which is what Jackson just said. So we don't need to test anything out here because this is going to be the end behavior, which is what that box on the last page is all about. And the same thing over here. We don't need to test over here because this depends on the degree. Whatever the degree is going to decide this piece. And so I look at that first page again. Let me put that first page back up. This is the end behavior page, right? And I'm looking at this polynomial, and it's got an odd power. It's got an odd degree of 3, and there's a leading coefficient of 1. And so when I'm looking at this, that's this situation where we have an odd degree and a positive leading coefficient. And so the right end is going to point up, and the left end is going to point down. And so let me write that down, and then we'll draw it. So this, from this, we know number 3 is going to be the end behavior. The end behavior, we have a degree 3. So the leading term, first of all, is x cubed, is 1x cubed. This has an odd degree and a positive coefficient. And so that implies that the left end points down and the right end points up. And so then we add that to our graph. So the left end points down and the right end points up. And that's what this graph looks like. Think about why that end behavior is true, right? X cubed is what really matters because when you plug big numbers into x cubed, it takes over. When you plug big positive numbers into x cubed, they stay positive, right? That's why the right side points up. When you plug big positive numbers in there, x cubed stays positive, and so it stays positive. But when you plug negative numbers into x cubed, they stay negative. And so when you plug in like -1,000,000, it's negative it's negative 1,000,000 cubed. And so this thing goes down because the negative numbers stay negative when you plug them into x cubed. Right? So there's those 3 steps. We find the zeros. That helped us list those 3 points. We test a number between them to decide whether we go up or down. And then we look at the first term, or the leading term, to figure out what's going to happen on the edges. Questions? Because when we plug a 1 in here, we'll get 1 cubed, which is 1. 2 times 1, which is 2. So we'll get 1 plus 2 minus 8. And so that's going to be 3 minus 8, which gives us negative 5. Does that make sense? Does that notation make sense? Like plug a 1 in there? Yeah, you plug it in for x, exactly. And then so g of negative 2 was plugging a negative 2 into the x in there. Yeah, I didn't go over the details on that because I know that you can do that, but that's what that notation means, and I plugged those numbers in there to figure that out. Yeah. Other questions? I'd like you to give this one a try. See how far you can get. We'll reconvene in about 5 minutes. At least try to get the intercepts down. Right? So at least factor this thing and try to figure out what the zeros are. And then, if you have some time, plug some numbers in between them and see what you get. I'm going to start writing some of this down too in case you're stuck and to save time a little bit. Let's see how far you can get with this one. If this makes sense, hopefully you can do this one yourself. Right, so you can factor out an x squared out of this one. Yeah, that was so in this one. So in this next line, it should have this up front. So Jackie, this is, see how this line has the x with it? I don't think you had that on your paper. So I did that already. No, we'll get Yep, that looks good. So I'm writing down the zeros here. Hopefully you got these. Guys get 2, 0, and 1 out of there. Whoops. I'm going to set my table up and then reconvene in a minute here. It's actually, so let's reconvene. These are a little tough to plug in without if you don't have a calculator with you. In a test or something, I would not make it so that you have to pick a fraction to plug in. But in this particular one, you know, when you factor it, you end up with x squared, x minus 2, x minus 1, and so you get 0, 1, and 2 out. And so when you pick numbers in between those numbers, they have to be decimals or fractions, right? So you could do 0.5 or 1 over 2, whichever one you want to think of, or 3 halves or 1.5 to test there. Do you guys get those zeros though? Is this okay? And so we want to make a table and test some numbers between them. Again, I apologize for making it a fraction one, but sometimes you got to do fractions. If we plug that 1/2 in, I'll just cut to the chase and tell you that we get 3 over 16. The exact number is not important. It's not super important. It's nice to know what it is. You know, if we know what the number is, we can like label it and notice how this one I made the left peak bigger because it went up to 16, and the left one, or the right one, only went down to 5. And so that's helpful in that case. But the real important thing is we just know whether or not it's positive or negative. Because we want to know, on this graph, I know it crosses at 0, I know it crosses at 1, and I know it crosses at 2. And I just need to know whether it goes up and then back down, or down and then back up. And so since this is positive, we're going to be above the x-axis at this point. And so between 0 and 1, we're positive. And so I'm going to go up to 3 over 16 and then back down to 0 on that first piece from this. When I plug in a 1.5, you get a negative number, negative 9 over 16. And so that means we're below the x-axis. And 9 over 16 is obviously 3 times more than 3 over 16. So let's make that more negative looking. So it goes down here and then back up. Those two pieces all right? And then as a reminder, we don't need to test anything in the ends because this is going to be the end behavior over here. All of the end behavior comes from the leading term. And so when we think about the end behavior, we just think about the leading term. So the leading term in this one is x to the 4th. Is 1x to the 4th. And so it's got an even power and a positive coefficient. Right? So this has got an even power and a positive coefficient. And so that implies, let me go back to the last page. Right? Even degree, positive coefficient, that's this picture. Right? Even degree, positive coefficient. And so both of the ends point up. In other words, think about what x to the 4th looks like, right? X to the 4th has both ends pointing up. And so this means that both ends are going to point up, right? So this means that ends both point up. And so we finish off this graph by making both the ends point up. And that's what that one looks like.